Welcome back, breaking down the development pro forma, where we dissect, we slice, and we're dicing up every cost and every line item in a development pro forma so that we can mitigate our risk and then execute and make money on those promotes. It is time. All right, in the last episode, we talk about the unsung hero, the man who's got to understand the below grade, the geotech engineer. Today, we're talking about the skeletons in my closet. No, I'm talking about the skeleton that holds up your building. And who's responsible for that? None other than the structural engineer. Now remember, I'm always a stickler on licenses. That's a PE, professional engineer. They got schooling, they got tests, and they licensed by the state. So I'm talking about the structural, that one who's responsible. It's not all mathematics. They actually got to take our building from below the ground and get that bad boy up. Episode number 4, the structural engineer. All right, so what is the structural engineer's responsibility, right? They are, I keep saying it, the structural system of the building, but what does that really mean? We got columns, we got beams, we got slabs, we got outside walls and interior walls. Everything that holds that building up and transfers the load above grade back into the ground without it settling differentially, which we'll get into. All right, so why does that matter? Why are we talking about the load above grade and then transferring that into the ground? And that's because the earth below, which we talked about before with our borings and test pits, is irregular. It's got different pockets of different things that are occurring. Maybe it's got clay over here, it's got rock over there, right? But what could happen if it's got different clay, it's got different sand, it's got different fill? What does that really mean? That means that the bearing capacity, its ability to bear the weight of above grade changes, and it's different, right? And you want a uniform slab. Why? If one cracks, you got some problems. Think Leaning Tower of Pisa, right? Which is called uneven settlement. So we don't want cracking, we don't want leaning, and we certainly don't want any type of structural failure. So the structural engineer's job is to make sure that the building settles evenly, transferring the loads back and forth throughout that asset down to the actual footings, and that it was within tolerance that it can accept that limit, and your building is flat, level, and everybody's happy. Now, what I said sounded kind of simple, right? Little math, little understanding below grade, and boom. Now let's add a little complexity to that little equation that we were talking about. So maybe you're in a stadium. Maybe you don't want columns in the retail space. Maybe you got a floating cantilever that you got to go over the buildings because you bought the air rights, but you can't drive columns straight down. Maybe it's a rooftop pool. Who knows? But all of these design changes affect how the forces impact the existing structures that we were talking about. The slabs, the columns, the beams, right? Okay. So that means that sometimes you got to use different structures, moment frames, post-tension concrete, creative use of materials to support long spans and unconventional layouts. And that's what the beauty is of a building. Without those things, it wouldn't be interesting, but the structural engineer has to take that information and then design for it. Now, they also have to do it within the building code. We talk about it all the time, within budget, right? And then without over-engineering something. Now, the question is why? What are we so concerned about? Because just because you can design a structure that's feasible on a design does not mean that those extra costs for those random moment connections, dropped arches, dropped beams, don't make it so expensive that it's not accretive to move the project along. So they got to finesse it. They got to finesse what the architect wants, and they got to make sure that building isn't going to settle differential. Gets a little more complex than just a normal mathematical equation, am I right? Structural engineers also responsible for selecting the material systems of that building. And that's a critical decision, I'll tell you why. If we have tariffs on steel coming out of a country, let's say now Canada or China, the cost went up. So is it more accretive to use a different material that's local, right? So the point being is they now have to have an understanding of the different materials and the impacts of the cost on those materials, right? So now, concrete, what's that great for? Great for mass, stiffness, and the fire resistance, right? Because in high density urban areas, we have massive fire codes. We can't allow fire to spread. Concrete is amazing at that because it's a non-combustible material. How about steel? Where do we see steel? Long spans, right? Because we can create these trusses, which are these massive sort of webs in our beams in order to span huge distances to have less columns, right? Where would you want that? Retail, at an arena, a theater, right? And how about this? Speed of construction. You get shop drawings for steel and they get manufactured elsewhere, so it should be like Legos and an erector set. Is it always like that? No, but it should be. And it's flexibility. You can change different shapes of steel that still have structural components to it. What else? Then we got light gauge framing. You're not going so high. So you want light gauge. What's light gauge? It's cold rolled steel. It's manufactured steel. It's not hot. It doesn't have to go through liquids into a liquid form and then get solidified. It's called cold rolled steel. Now that's good for mid-rise buildings, right? You're not going that tall. It's easy, it's lightweight, gets erected right in the field. And then last, we got this new, and we're seeing it all over New York and elsewhere in the Midwest, timber construction, increasingly popular for sustainability and aesthetics, right? Always looks fresh, it looks dope, but let me tell you something, more expensive. So this is the point. Each material has a different property. They're responsible for understanding the economics, what its capacity is for structural weight and its ability to carry specific loads, and its availability in that moment. So it gets a little bit more complicated. The structural engineer isn't just a mathematician. Now, what's another aspect of it that we don't really think about? Expertise in the field. Specific states, specific areas have specific crews that are used to specific materials. If a structural engineer designs something that can't be implemented in real time by a subcontractor, that was a waste of time in design. We see that all the time. When you have subcontractors that are working in wood and then you give them light gauge, that actually increases the cost because they don't understand what their waste is going to be or their ability to execute it. If you're in a place that's all steel and then you do want concrete subcontractors, will there be a market there? Will there be over demand? So a structural engineer has to understand the availability of the materials, the credibility of those crews in the field, and also achieve what the architectural design was looking for. So at the end of the day, it's always easy to think of structural engineers as math guys, math people. Loading diagrams, stress testing calculations, but the best structural engineers out there also bring real-world experience and judgment. They know what works in the field. They can go out to the field, create a quick SK, and actually make a decision that does work. Obviously, I go back to the drawings and we got to refile it, but they're also in the field solving issues that actually occur. They understand the contractor's perspective, they understand the sequencing, they understand the budget. They can value engineer a project without ever compromising its safety. We deal with it all the time because, as we discussed earlier, if you have specific details that are so expensive it's not feasible to build, you're never getting that building out of the ground. Finally, and what's most important to everybody, where does it show up in our underwriting and our pro forma? Okay, so basically it shows up in two different ways. We talk about it a lot. The soft costs, right? Engineering fees. They got to cover the structural analysis, the construction drawings. How do you make an application to cost? Now, if it's a simple building, urban infill, not that tall, it's a price per square foot. But as you get more complex, post-tension, pre-tension, any type of high rises, it gets much more expensive. So we use a price per gross square foot. And then it's similar to what we think the MEP engineer is. So we make the application that in low density single family, it's much less, just a quick consulting fee. But in high rise construction, we're looking at anywhere from $2 to $350 a foot on gross square foot when we're underwriting our structural engineer. Now the second thing is, and it's much harder to tell, and it's not really the structural engineer's responsibility, but it is yours as a principal developer, and that is, what is the cost of the structure in the field? That's your hard cost. We'll get into that in another section of this in a much later date, but the structural engineer, his design impacts what your cost will be for superstructure in the field. So one misstep here, over designing, sets you back months and months because you're designing and you're coordinating drawings today, bidding them for a future that doesn't exist yet. So the structural engineer is much more important than just someone designing. They also impact the future costs of your project. Choose wisely, choose someone who has experience, and choose someone who actually knows how to get it done. Everyone on your team must be Machiavellian, which means the effective truth, the result of an action. Do they have the experience to know that their design can actually get built within the geographic region that you are. One misstep, it'll be too expensive, and you're never getting it done. So next time when you walk into a building and you see some wide, expansive lobby with high ceilings, you know a lot more was put into it than just some math calculation. Or if you see some glass box suspended over the sidewalk in Midtown Manhattan, you know there was a lot more into it than making glass into a structural item. They work in their background. You never hear any press about them, but their decisions shape every square foot of the building you're trying to develop. Next time in our next episode, we're going to get into, I like to call it the organs of the building, the MEP engineer, mechanical, electrical, plumbing. They also do HVAC. I don't know why it's not in the name. I didn't do this, okay? Someone else did. I'm just spitting facts for you. So pay attention, sit down, wait up for the next episode. And at the end of the day, we do this to show you that we have an understanding of the construction and development process, especially in the way that you underwrite that deal so that we can find you the right capital to execute on it. Or maybe sometimes we'll be the developers with you. Talk to you soon. Peace, everybody.